Hey guys, Professor Doney back. We're continuing talking about Newton's three laws of motion, and we're looking or analyzing this 10 kilogram box that's sitting on the table or the floor, and it could represent anything, our car, anything we're trying to slide across the floor, anything is just trying to move across the surface. Alright, so Newton's law is continued, and what we have here is a 5 to left, a 10 up, and a 10 at an angle here at 30 degrees. Okay, that little angle right here is 30 degrees. So how are we dealing with these? We want to know if it moves. So this question might say find the acceleration in the x and the y. Find out, does the box move? Anything like that. So what we need to do again is first draw our free body diagram. And again, the free body diagram basically takes the body or object and removes everything touching it. So since we got rid of a floor, we have to put the F of n in there. That's the normal force. Since it has mass, we have to put mg. Alright, as long as those two balance, it's not going to move. We also have a 5 back here, we have a 10 going up, and then lastly we have this 10 acting at an angle. And how are we going to handle that? Well, just like we saw in the projectile motion, anytime there was an angle which made it a vector, we want to break it into x and y. The x component is going to be 10 cosine of 30, which comes out to be 8.6 that way. And the y component will be 10 sine of 30. If you remember looking back at projectile motion, you can check that. That gives us a 5 up. Alright, so now that we've broken those into horizontal and vertical, I can put the 8.6 here as a horizontal, and I can add the 5 as a vertical. It's 5, because those two represent that vector as the components or sides of the triangle. Now we're good to go. Now again, we're going to start off looking in the y direction first. Again, because eventually with friction we need to know F of n. We're going to just check to make sure this box doesn't lift off the table or something weird. So call positive up. We're going to sum all the forces in the y direction equal to 0. Again, we're going to assume it's not going to move. Math will tell us if we don't. We'll see that in a later problem. So I have a 10 up. I have a 5 up. I have an F of n up. I have an mg down, and they all have to equal 0. 1, 2, 3, 4 up and down have to equal 0. I solve for F of n. I'm going to get mg, what's that, minus 15. Since that's 10 for mass, 9.8, that comes out to be 98 minus 15, that comes out to be 83 newtons. It tells us this box appears to weigh only 83 newtons. Why? Because we have this extra 10 and 5 making it lighter. Alright, it's if I was a wrestler and I could reach up and grab the ceiling and pull on something, the scale would think I all of a sudden lost weight. So anyway, we're good. There's that's greater than 0, so it doesn't cause any issue with this thing leaving the table. So let's look in the x direction now. Alright, horizontally we can look at this, and by inspection, as engineer would say, hey, there's more to the right than the left. This thing is gonna move. So I'm going to go right to Newton's second law, because I'm pretty confident that 8.6 will beat the 5, causing this box to move to the right. So I'm going to sum forces in the x direction equal to ma, and that'll give me an acceleration in the x direction. So I pick positive to the right, just standard. That makes it a minus 5 there. This guy is a plus 8.6. A mass of 10 for the box still up here. Times a, we find out the acceleration x direction is what? 3.6 divided by 10, so 0.36 meters per second squared. What does that tell us? It tells us, hey, the box did move horizontally, and this is its acceleration. Now I could go back and use my chapter 2 equations, all those ones I'm sure you love by this point. 2/8 delta x and the delta x equals equation, and I can find out like how fast it's going after 10 seconds, how far it went when it reached top speed, all those things. So there's a good deal with Newton's laws with a bunch of different forces, mainly looking at when there's an angle associated. So we're going to continue with this, and we'll probably have one more of these problems and see about what happens when the box lifts off the table. Alright, see you in the next video.